So, thank you everyone for coming to join us for the next installment in our ASRG webinar series, the COVID-19 approved version of the ASRG meetups. As many of you hopefully already know, ASRG stands for the Automotive Security Research Group. We are a global group that consists of independently managed chapters all over the world in, I want to say every continent except for the really cold ones on the top and bottom of the earth. That don't really have a lot of people on them. But we're essentially dedicated to making knowledge and information about the automotive cybersecurity industry accessible to everyone. As such, ASRG is free to participate, and anyone interested in learning more about the automotive cybersecurity industry or contributing in some way to the community as a whole is welcome to join. It's free to join, free to contribute, so on and so forth. If you're interested in learning more, I encourage you to follow us on LinkedIn or Twitter. The QR code shown on the screen now will lead you to those respective links. And of course, you can always follow along for more news at the ASRG.io website. Quick look at the different locations we have all over the world. We have, several in the United States. A lot of the United States ones originated, I think Detroit was the first one in the United States. That's actually where I started with ASRG. But many in Europe, a couple in Africa, up there in Egypt. We have one branch in Australia. Also, only one here in Japan. That's the one I'm actually presenting out of. I'm not presenting per se. I'm hosting. Dennis, who will be joining us in a second, is the one who will be presenting for us today. But the point is that very close by you, there likely is an ASRG chapter. And if there isn't one, you can get in contact with us if you're interested in starting your own chapter in your own area, and we'll be happy to help you get started. A little bit of background information about me, your host for today. My name is Kamil Gali. I'm the coordinator for ASRG Japan, or JP, I suppose, is the actual type up there on the screen. I'm an automotive cybersecurity architect at a company called White Motion. It's a very low-key, not very well-known startup owned by the larger automotive supplier, Marelli, the Italian automotive supplier. My email, of course, is up there on the screen. If you have any questions or complaints or criticisms about my performance tonight, by all means, please go ahead and send me an email, and I'll be happy to read it. But for today, the presentation for today is going to be given to us by Dr. Kengo Oka. He will be presenting on Fuzz Testing, Automotive Systems, Process and Practice. So he will be taking some time out of his busy schedule to talk to us about what he does at Synopsys. With automotive cybersecurity and how it's important for the industry. And just before we get started, a quick look at some upcoming webinars that will be happening later on in case you want to mark any of these in your calendar before we get started. We have U-Boot versus Security Cyber Garage, IDPS from the vehicle to the VSOC, and V2RF, assessing cars RF communications. So, of course, if you have your own presentation or paper you'd like to present to us, by all means, please contact us at the cfp@asrg.io link down there. And now I am going to go ahead and switch over to the call. So, Dennis, you're on screen right now. Go ahead and give us your introduction, and then I'll let you take things away.
Thank you very much, Kamil, for the introduction. Hi, everyone. My name is Dennis Kengo Oka. I'm a principal automotive security strategist at Synopsys. And I want to thank the ASRG for inviting me to give this webinar. Today, I'd like to talk about fuzz testing automotive systems. And I want to go into both the process and practice and talk a little bit about some details, both for organizational level, but also some technical topics. So before I begin, I'd like to just give a very brief introduction. So I started automotive security in 2006. I got my PhD from Chalmers University of Technology in Sweden. My work was focusing on the connected car. And then I've been working with a number of different OEMs and suppliers over the years, looking at different security processes, security activities, improving security in their products, and so on. I'm also involved in a number of different standardization activities, the best practices activities. For example, part of JASPAR, LTA TR68, part of the Open Chain Automotive Working Group, Optane, and so on. And I've also been active in writing a number of different research papers and presenting at different events, such as SA World Congress and SCAR and Embedded World and so on. And finally, I'd just like to give a short note here on a book that I recently published called Building Secure Cars, Assuring the Automotive Software Development Lifecycle. In this book, I focus on the entire development lifecycle, and I go through different cybersecurity activities that organizations need to think about, and also go through a number of practical examples. So if you're interested, please feel free to check out the book. So with that, I'd like to move on to today's agenda. There are 3 points I would like to share with you. First, I want to talk about how integrating fuzz testing into the process provides added benefits, and we'll go through what those benefits are. I also want to highlight some of the common challenges and pitfalls that exist when performing fuzz testing of automotive systems today. And then based on these learnings, I want to talk about how we can build a test environment that allows for continuous fuzz testing, which allow you to do testing faster and earlier in the development lifecycle. So let's start with the first point. And I'm sure all of you know this already, but I wanted to give a very brief introduction to make sure everyone is on the same level. So as you know, we have the major trends in the automotive industry, often noted as the acronym CASE, which stands for connectivity, autonomous, shared and services, electrification. And what all of these trends really lead to or involve is really more software. There are more attack surfaces. There are more valuable targets to store more valuable information. So we have a growing need for security. And we see this also now with the upcoming standard ISO SA 21434, but also regulations such as the UNR 155 on cybersecurity. So with that background, I like to go into the process and see how can we fit fuzz testing into our engineering process. On the left-hand side, we see the typical V model from ASPICE. You have different requirements engineering steps on the left-hand side, and we have our integration and verification steps on the right-hand side. And if we now consider cybersecurity mapped onto this V model, we get something like on the right-hand side. So for the left leg, we have TARA, our threat analysis, risk assessment. And then on the right leg, we would have our testing approaches, including functional testing, vulnerability scanning, fuzz testing, penetration testing. Excuse me. And in today's presentation, I want to focus on fuzz testing. So we'll go through that with a little bit of background of what fuzz testing is. And I'm not going to read this. You can read it yourselves, but just to highlight some keywords here that we're sending intentionally invalid data. And we're trying to trigger an error condition or a fault in the product. And these error conditions could lead to exploitable vulnerabilities. So the goal with fuzz testing is try to send as many as possible different malformed input to a target system, observe how it behaves. If it crashes or it does something unintentional, then we can explore that further to see if that could actually lead to a vulnerability, and then we need to fix it. This is also a typical approach of how attackers go about when they try to attack a new system. They will perform fuzz testing to identify new vulnerabilities in those systems. So many of you know this already, but also to give a little bit of background on fuzz testing. So as I mentioned, it's a technique used by black hat hackers, security researchers to find new vulnerabilities. And as mentioned, you have your target application. You would send in various input to it. Anything that's outside certain boundary conditions, illegal values, good checksums on bad data, and things like that. And what you then observe on the target system or the application is any anomalous behavior, resource leakage, crashes, and so on. So if we look at how a system typically is implemented, we have the requirements for that system, and that's the intended behavior. So it's depicted here with this blue circle. Then we have the actual implemented behavior. So that's the program code, how the developers have tried to fulfill these requirements. Now, ideally, these two circles should be overlapped. But as you can see, the yellow circle sometimes may be a little bit outside of the blue circle. So we have implemented functions here in this part that are not really part of the requirements. And we may also have missing functionality that are part of the requirements but not implemented. So for that part here, the missing implementation, these are the positive test cases. It's very easy to test for this because you know there should be a certain functionality, and if it's not there, then we can find it. On the other hand, the part on the right-hand side, anything that's implemented but not part of the requirements, these are negative test cases. And this is really hard to test for because we don't really know what's been implemented, but we still need to try to find anything that's not part of the requirements. And this is really where fuzz testing can help to identify and test for anything that's implemented but not part of these requirements. So as a very simple example, we can imagine a X509 certificate parser. So the test case here, the positive test case, is sending a valid X509 certificate and see if it gets parsed correctly. But to test the negative test cases here, we need to have millions of invalid certificates to see if any of these will be processed somehow. So that's really the hard way of testing this. And this is where fuzz testing can help by generating these fuzzed certificates automatically. So to give a very simple example of how fuzz testing have been used in the past to find vulnerabilities, there's a very famous example, the OpenSSL Heartbleed vulnerability. And perhaps all of you know this already, but you have this heartbeat functionality in OpenSSL. You have your test tool. This could be your typical functional testing. You send your message here, hello, with the size 5 bytes for this message. And in the server, this data will then be stored, and it will then respond with the 5 bytes, which is the hello message. So we know that the server is alive. Now, you can imagine now if we do a fuzz test here, a negative test case, where we have the same content, hello, but the size is now something invalid. We have 65535, which is not a correct message. But if we send this now, the server will read out this many bytes, the 65535 bytes from the server memory, and respond with that. So we see there's a normal response to this request by sending a abnormal request. So that's a very simple example of how you can trigger some invalid behavior in a target system. So why is fuzz testing important? Well, we have the new cybersecurity engineering standard, the ISO SE. Currently, the FDIS version is released. And there are requirements on verification and validation defined in requirements -10 and requirements -11 clauses. There's also a recommendation that testing should be performed to confirm that unidentified vulnerabilities and weaknesses remaining in the component are minimized. And fuzz testing is mentioned as a test method here in the RC 10-12. And we also have requirements that identify weaknesses shall be analyzed and identify vulnerabilities shall be managed. So considering these requirements and recommendations, we can expect that more automotive companies will start to implement fuzz testing as part of their security engineering process. So in doing that, we first need to understand what are the common challenges with fuzz testing. And we'll go through a few examples here. So first, we see here As shown in the V model that I showed on the earlier slides, fuzz testing often occurs late in the development lifecycle. We also see that fuzz testing is often performed by, for example, a security tester. So you have a manual activity being performed late in the development lifecycle, which leads to any issues you find this late in the development lifecycle is also very costly to fix. In addition, because you have testing performed late in the development lifecycle and often only once because of the manual effort it's required, you typically have a limited test environment. It might be just a simple tool and a simple setup to be able to just run the test that you need to do once. And because of this limited test environment, you typically also only achieve limited coverage for the testing, and you might miss a lot of potential issues in the product. So to overcome these challenges, one way is to integrate fuzz testing as part of the process so you perform it systematically. And I'll go through some of the benefits in doing so. So first, if we have fuzz testing performed systematically throughout the process, then we can shift left and have fuzz testing performed earlier in the development lifecycle, and we can have it performed continuously. To do so, we need to move away from having a security tester manually doing the testing to automate the testing. So really running the test in an automated test environment where you can run this continuously and throughout the entire test process. Because we run testing early, we run it automated, any issues we can find early on and fix them early as well, which reduces the cost for fixing the issues. And then because we want to set up this automated test environment, and because we run it so often, we need to make sure we have a proper test environment in place. We have all the necessary tools, additional input that is required to make the system work as it should, any other automation servers and bug tracking systems and so on are integrated into that test environment. And then finally, because we have this more comprehensive test environment, we can also achieve greater coverage. We can go into testing different test scenarios, putting the target into the right test states, and perform testing much more often and throughout the entire development process. So to give a very simplified example of how this could look like, we have here on this slide the top portion showing fuzz testing late in the development process, and the bottom part showing fuzz testing continuously over the development process. So in the example above, we have, for example, development performed over 7 weeks, and then the last week we dedicate to fuzz testing. So let's say we can have a security tester perform 8 hours of testing over 5 days for 1 week for a total of 40 hours of fuzz testing. In the bottom example, we have fuzz testing being performed continuously, for example, 8 hours every night. So we can perform fuzz testing overnight, receive results in the morning, and then the development team can start fixing any issues early on. So assuming here we again use 8 hours of testing per day, over 5 days, over 8 weeks, we can achieve 320 hours of fuzz testing. Because we automate testing, we can also fuzz test over the weekend if we want to and increase this to 7 days. And if we wanted to, we can increase the 8 hours to 24 hours if we wanted to as well. So this number can really increase more than the 320 hours. And another point to mention here is that because fuzz testing is now spread out over the entire process, we can also use this last week to do any additional development or perform any additional fixes. So by doing fuzz testing continuously over the process, we achieve a much higher coverage and more time to do testing. So I want to go back to the process again, the V model, and show how fuzz testing can be performed within this process as well. So there are two levels where we can perform fuzz testing. The first one is the software unit fuzzing. So we can do this on the SWE5. So when we do our software unit fuzzing, we can target, for example, X509 certificate parsers, our custom rating parsers, any other data input, config files, anything that's being processed by some kind of parser in the software. Then we have our second level of fuzzing, and that occurs on the sys4 level, the system interface fuzzing. And here we look at the different communication protocols, such as CAN, CAN-FD, and now we have UDS as well. And then we have the Ethernet stack with IP, TCP, TLS, and DoIP. So this allows us to do testing on two different levels where we can early on find issues with specific parsers during the software unit fuzzing. And then later on, we can focus more on the system interface fuzzing during the sys4. So I want to give an example of how this can look like. So if we take a look at the secure communication function. So on the left-hand side, we have the system interface fuzzing. And on the right-hand side, we have the software unit fuzzing. So if we split this secure communication function into these two parts, we have on the unit level, the X509 certificate parser. And on the interface, system interface level, we have the TLS interface. So these two functions can be tested separately. So the way we do that is we set up our fuzz testing tool. We can start testing the X509 certificate parser for the software unit fuzzing. And in this case, we will then generate fuzzed certificates, malformed certificates that we can then input to the parser. And then the second level is the TLS interface. So at this step, we can focus our fuzz testing on the TLS communication, on the different parameters, the different fields in that communication. Now, as a note, we could also test the TLS interface here with malformed X509 certificates. But if we can test that early on here on the right-hand side for the software unit fuzzing, we can reduce that test time by using only valid certificates for the TLS interface and focus on fuzzing or putting anomalies in different parts of the messages and keeping the valid certificates because we know the certificates have been tested during the software unit fuzzing. So that's one way of separating and testing to allow you to do part of the testing early on and then focus the rest of the testing later on different parts. So to show some details of how this would look like, the SWE5, the software unit fuzzing, in this example here, we would generate fuzzed X509 certificates. And they could look like something like this, as shown on the right-hand side. So we can generate a large number of these fuzz certificates. They will have some kind of malformed data within that certificate, and we feed them to the certificate parser to see how it handles these malformed certificates. And then for the sys4, the system interface fuzzing, we then include valid certificates here and instead focus on fuzzing other parameters, other fields here in the communication. So this again allows us to separate the target of the fuzzing, having the parser being tested during the software unit fuzzing, and then testing the communication during the system interface fuzzing. So next I want to move on to discuss some of these challenges in more detail. So let's take a look at a typical test environment for fuzz testing. We have our fuzz testing tool here on the left-hand side, and we have our software system in the middle that we're testing, and there's some kind of interface that we will be testing for fuzz testing. So this is where we provide our malformed input. Typically, there are two ways where we can monitor for exceptions on the target system, and they're called in-band instrumentation and external instrumentation. So in-band instrumentation, you look at the communication that's being fuzzed, and external instrumentation, you would look at other external interfaces on this target system that you can monitor. And feedback regarding any discrepancies, any exceptions on the target system can then be provided back to the fuzz testing tool, stating, for example, that this particular fuzz message caused an abnormality or caused an exception on the target system. So let's take a look at an actual example of a practical example of this fuzz testing environment. So here on the left-hand side, we have a fuzz testing tool called Defensix. We now have our communication bus using CAN bus here, and we have an ECU as our target system. So as mentioned before, we have the in-band instrumentation and external instrumentation. In-band instrumentation we can do with the fuzz testing tool Defensix. Because we send fuzz messages on this CAN bus, we can also monitor that CAN bus to see if there are any exceptions occurring on the ECU. So one simple way is to listen to the CAN bus, where the ECU typically would send out some periodical messages. Let's say it sends out certain CAN IDs with a 100 millisecond cyclic message. Then we can observe whether this message is being received every 100 milliseconds, or if due to some fuzz messages, that message is now omitted or it's been delayed. Then we can detect that something might have happened on the ECU that caused that message to be delayed or caused that message to not be sent. For external instrumentation, we can use various tools here. We can use hardware in the loop systems. So we can use different test tools, debug tools, or also something we call agents, which would be pieces of software running on the target system that will monitor certain aspects of the target system, where you can monitor, for example, the memory or the CPU usage of a certain process. And then you can feedback this information back to the fuzz testing tool if you detect that there's a certain exception. So that's the typical test environment that you can set up. And now let's take a look at what we often see in the industry today. And that's what we call standalone fuzzing. And in this case, we don't have this external instrumentation. We only have this simple test environment. As I mentioned before, one of the challenges, we see this limited test environment. We only have the target system, and we may only have in-band instrumentation as the way of detecting issues. So there are a few practical challenges with this approach. First, we may not be able to put the SUT, this system under test, in the correct state for testing. What I mean by this is the ECU here may require some rest bus simulation. It may require some input on the different pins here on the ECU for it to behave in the correct way. Maybe you need an ignition on signal. Maybe you need some speed values, or you need some other information that is typically sent from other ECUs to put this target ECU in the right state. Because we also only look at the in-band instrumentation here, we may not detect other exceptions occurring on the ECU. For example, it might be outputting some data or some signals here on the other pins that we can't detect because we're not monitoring them. So we may actually miss a number of different exceptions with this limited test environment. And then finally, with this limited test environment, we're not able to automate the test process. You can imagine if we're trying to fuzz test over 8 hours, for example, overnight, if the ECU crashes within the first hour, we don't have any way of resetting the ECU, telling the fuzz testing tool that the ECU crashed on this particular fuzz message, continue testing after that message and proceed with the testing, it will just stop here because there's no way to detect this and reset the ECU. So that's a real challenge in having these limited test environments where you don't have full control of the target system. So to sum up these challenges here, testing is time consuming. It can take days or weeks depending on the protocol, the interfaces you're testing. It happens late in the development life cycle, which also means it only happens typically once because it takes so long to do it. Often these systems are difficult to instrument. That is, you need some kind of additional input to put them in the right state for testing, or you need to monitor other aspects of the target system to detect exceptions. And you may need your hill systems, your hardware loop systems, the rest bus simulation, and so on. And another typical challenge we see is when you do testing on hardware ECUs, like the prototype ECUs, you need to wait until you actually have access to hardware, which again is typically late in the development lifecycle, and any issues you find at that point may also be very costly to fix. So with that understanding, I'd like to move on to the third point here, where I like to share how we can build a test environment that allows continuous fuzz testing to detect these issues earlier in the development lifecycle. So first, just to give a general overview of CI pipeline here. So typically we have software from various sources. We have our CI, or continuous integration step here, typically using tools such as SAST and SCA. So your static application security testing and your software composition analysis tools. Then you have these results shown in some kind of dashboard, or they generate some kind of reports of issues they found. And then you send this back to your development teams and they can fix these issues. Now, this loop is often very short. It can be within minutes or hours, depending on the size of the software. But this CI step here is really to close the loop quickly, give feedback to developers early during development. I've separated the testing here into a separate step called CT, continuous testing, where we then have our fuzz testing. And I'll talk about this a little bit later on, but we will have our software and loop environment here using a virtual hardware, virtual ECU. And similarly, we do testing. We get results in some kind of dashboard or generate reports with the results. We send this back to our development team so they can fix the issues. But as you can see here, this bigger loop, because of the testing time, we typically see it take hours or even days, depending on the protocols or the interfaces that we're testing. And that's the reason why this CT loop is outside of the CI, because the CI is much faster. So it's better to have a separate loop here for the continuous testing. And the goal here is really to find all of these issues early on while you loop around here, shift this error curve left so you find and fix the issues early on. And then finally, you go to your release with a product that has hopefully as few vulnerabilities in it as possible. So briefly, just want to share a little bit about the CI step. So what we do here is, example using Jenkins. We have coding on the developer's PC. What they can do is they can run a real-time SAST in their IDE where they can find any particular issues while they're coding. They check in their code into a repository. Here we can do an incremental SAST to see any issues found in the code that was checked in. And then using Jenkins, we get the latest code from the repository. We do our build. Here we can do a full SAST because now we have access not only to a single developer's code that was checked at the top part, but also all other developers' code. So we do a full SAST here. And then also we do our SCA to identify any additional vulnerabilities in, for example, open source software components. So this is something that can be run in this smaller loop that I showed on the previous slide, where you can continuously give feedback to your developers. So with that, I'd like to talk a little bit more about the CT step here, the continuous testing step. And the way we want to go from is this standalone testing that I explained before. As you can see here on the screen, we have our testing tool here, the Fuzz Testing tool. We have the CAN bus as the interface we're testing on the target ECU. And we typically only have our in-bed instrumentation. That's the standalone test setup. And we want to move from this setup to a continuous testing. Typically, when you do that standalone testing, as I mentioned before, you are limited to using hardware. You have your prototype ECU that we test on. I do want to mention here that for continuous testing, before talking about the virtual ECU and the SIL solution, I want to mention that it is possible to do continuous testing on the hardware ECU as well, like on a prototype ECU. So we would need our external instrumentation here. We would need our Hill system, our test tool, and so on to allow us to do continuous testing. And I'll share a little bit of how that can look like. So while I talk about the possibilities of doing the continuous testing on hardware, we'll also see that it's very challenging to do it. And that is going to give us the motivation to move to using SIL, our software in the loop system instead. So here again, we have the developer in the top left corner. They're writing the code or generating code based on models. We get our C code, and then we build this for our target ECU. We get our hex file, and then typically we have to flash this then to our ECU. And then we do the fuzz testing on the ECU. That's typically how we see the testing happening today. And again, you can have your prototype ECU here. If you want to use the external instrumentation to automate some of this testing, you also need to have your Hill system connected. And here you then have your feedback loop where you can provide information about any exceptions found during the fuzz testing. The challenge here with doing continuous testing on hardware using Hill systems is that typically this big loop here is going to take days or weeks. So it's very far away from this small, shorter loop you had with CI. You could do this big loop with CT, but it's also going to be very long before developers will get feedback from the testing. You also have the challenge that the hardware here, the prototype ECUs are limited. You may only have one ECU that you can do testing on. Hill systems also limited and costly. So you have very limited test environments that you can build using this approach. So that leads me to the solution using SIL, the software in the loop system. So what we can do here is we can compile our C code for a PC, or we can use a chip simulator for the hex file. And this means we can run a virtual ECU on our PC rather than on a real ECU. And then we can do fuzz testing of that virtual ECU. So this will be within our SIL environment. We run everything on a PC. We can do the testing earlier because we have access to the software and can do the testing without need for hardware. This means that this loop here is going to be much smaller, and this could be within hours or days, depending again on the type of test we do. But this continuous testing loop here is going to be much faster than doing the testing over hardware. And again, another benefit is if we're testing on virtual ECUs, we're not restricted to the limited hardware devices that we have for the bigger loop, which means that we can spin up, for example, 10 virtual ECUs and do testing on these virtual ECUs in parallel, again, to shorten this time that we need to do testing. So that's really the benefit of performing testing using the SIL systems. So I want to give an example here again using CI and Jenkins. So we had what I mentioned before, coding on the developer's PC, checking into repo, and then we get the latest code. We do our build here using Jenkins, and then typically we do our functional test here. At the next step here, we want to add fuzz testing. And the way we do that is, first we have to generate these test plans in advance. These are configuration files where we have to define, for example, the CAN IDs we want to test, or the IP address of the target system, or the port number that we want to test. So we have to prepare the test plans in advance so we know which protocols should we test, what are the parameters that we need to include for that specific target system. And then we can have Jenkins load these test plans automatically and perform fuzz testing in an automated fashion here by having Jenkins trigger and call the fuzz testing tool. So in this case, we don't need to have a security tester anymore. This can be done automated in the process. So I want to give an example of a test setup that we built for this fuzz testing on virtual ECUs. We have a fuzz testing tool called Defensix. We use a virtual ECU as the system under test. And then we have a tool called Silver, which is our software in the loop environment. So these are the three components that we use for the test environment. I'll briefly just explain these components. So as I said, Defensix is the fuzz testing tool. It can automatically generate these malformed inputs. It supports 250 plus test suites, and it can be used to test specific attack patterns for protocols such as CAN or TLS or the X59 certificates. Silver, as I mentioned, is the software in the loop system where you can then create these virtual ECUs. And the virtual ECUs are really the same software as the ECU that would run on the physical ECU, the hardware ECU, but you run it on your PC. So you have the same sources. You have you can also run the same hex code using a chip simulator, and you would have the same interfaces for other tools that you want to use for calibration and configuration and so on. So the way this test environment looks like is shown here on this slide. So we have everything here running on one PC. So that's the one thing to note, that we run everything on a PC here. There's no additional hardware, no additional ECUs, and so on. We have the fuzz testing tool Defensix here on the left-hand side, and we have Silver here on the right-hand side. In Defensix, we have our test script. We have our modified CAN injector. So typically, Defensix will send malformed CAN messages onto a CAN bus. But here, the injector is modified, so we send this over UDP. And Silver, within Silver, we have a Defensix module that can receive these messages over UDP and then send these onto the virtual ECU. The virtual ECU will then process these messages as CAN messages and then be processed within the right function within the ECU. So this virtual ECU is our system under test. It's again a software ECU running on the PC that we can test without running on a physical hardware ECU. For the external instrumentation, we see that we can also have rest bus simulation and other features here within Silver to make sure that we can put this virtual ECU in the right state for testing. We can reset the ECU if there's an issue found, so we can continue testing to automate the testing. And we do the exception detection here within Silver because we know what the correct behavior of the ECU is. We can monitor different parameters within the ECU. That sometimes is typically difficult to monitor on a physical ECU, but having everything within software allows us to monitor those specific parameters and values. And then finally, we can send this feedback back as external instrumentation to Defense6 and say, this particular fuzzed message caused this type of exception on the ECU, and here are the measured value, for example. Here's the state that was detected. So to give an idea of the test targets on these virtual ECUs, we have here on the left-hand side a typical AUTOSAR example of an ECU. So you have the bottom, the ECU hardware, you have the different drivers, CAN and so on, you have your MCAL, you have your BSW, your basic software, you have your ASW application software here on the top. Now on the right-hand side, we see how we can run this on Silver. So we have in blue are the parts that are virtualized within the PC. And then in yellow is the actual ECU software that's being run as is. So we can, for example, just run the ASW, the application software, and virtualize everything else underneath that. Or we can have a setup where we also test the BSW. So we virtualize just the OS and MCAL. So there are different configurations we can use depending on what we want to test within the target software. So to give an example of how that looks like, we can then generate a fuzz message. For example, over UDS, we have a security access. So we can generate a fuzzed security access message here with some malform data. And if we want to test the UDS implementation on a virtual ECU, we can then send this fuzz message to that virtual ECU that will then process that message. Again, this allows us to do this testing without having access to hardware. And if there are any issues, we can detect these issues early on and fix them before we have to flash them to hardware. The ECU, the virtual ECU running on Silver. Again, it could be different types of ECU you want to simulate or run here on the virtual environment. And you can also have visualization of the output from the ECU. So you can imagine we want to show maybe the speed, or we want to show the gear position or the RPM. So we can read those values out and then compare them to what is a typical normal value that is acceptable, and detect if there are any exceptions to those values. So again, we can look at both the visual representation of the ECU and the results or the outputs from that ECU, and also calculate different values that are being processed on that ECU and use that to detect exceptions. So just to show how this flow would look like, so we have Defense6 here on the left-hand side, we have Silver here in the middle, and then we have our SUT. This is the software on the virtual ECU, for example, our ASW or BSW. So first we have to make sure we put the ECU in the correct state for testing. So we generate our rest bus simulation and make sure that the ECU is in, for example, test state 1 or test state 2 and so on. We then send a message to Defense6 saying the ECU is now ready for testing, start fuzzing. So we start sending our first fuzz message here over CAN to the ECU. Again, this will be processed on the software on the virtual ECU. And then we can send a trigger here back to Silver and say, please check the ECU if it's behaving as it should. So we can get different values from the ECU. Again, depending on what that ECU is supposed to do, we read out those specific values, compare them to some threshold values or reference values to make sure that they are correct or valid. And if those values match, then there's no problem. So we go down and say that test case passed and everything's okay. But if there's a discrepancy here, the measured value is above a certain threshold, the ECU is not behaving as it should, then we send a response saying the test case failed, and we log this then in the log file on the Fensix. So this is a way where we can perform the testing, we can monitor the ECU, the software on the virtual ECU, compare it to different values because it's all in software, and then decide whether there's an exception or not. So to sum up these benefits of doing the fuzz testing on virtual ECUs, as I mentioned, it's more time efficient. We can spin up multiple instances of virtual ECUs, run the testing in parallel. We can run it earlier because there's no need for hardware, and we can really build this continuous testing loop. It's also easier to instrument because we have full access to the software within the SIL environment. We can input the correct values for testable states, the rest bus simulation. We can monitor the ECU, read out different parameters, different values from the ECU to detect exceptions. And then finally, as I mentioned before, the goal here with the continuous testing is we want to do testing as early as possible and as often as possible. So having this no requirement for hardware allows us to do this testing early on. As soon as we have the required functionality available, for example, as soon as we have the security access function available, we can start testing it. There's no need to wait for everything else to be built and then flash it to a real ECU and then do the testing for security access. We can do that on the virtual ECU early on. So that brings me to the last slide here, just to summarize what I talked about today. I talked about first part, how we can integrate fuzz testing into the process, the two different levels of fuzz testing we can do, and the additional benefits of automated testing, running it more often, shifting left, reducing the cost, getting a greater test coverage that brings. And then we talked about some of the challenges, especially at standalone fuzz testing, where you have challenges of putting the ECU in a testable state. You may not be able to detect exceptions because you have no external instrumentation, and you have challenges in automating the testing because you're not able to reset the ECU and reset or restart the testing. And then finally, I talked about this CT, continuous testing process, where we can then move from the hardware ECUs to virtual ECUs, perform testing much earlier in the development lifecycle, and put the ECU in the right testable states, monitor the ECU in better ways, finding issues earlier. One thing to mention is, although we can do the testing on a virtual ECU, as you saw on one of the slides, there are some parts that are virtualized that we cannot test on the virtual ECU. For that, we still need to do the testing on a physical hardware ECU. So I'm not saying that everything can be done on a virtual ECU. We still need to do testing on a hardware ECU. But if we can remove a lot of the testing that we had to do before and do that testing on virtual ECUs first, the scope of testing that needs to be on hardware ECUs is going to be much smaller. So we can save time by doing as much testing as possible on virtual ECUs early on, and then only do the testing that requires hardware, especially the lower level drivers, later on once we have access to hardware. So with that, I'd like to thank you for your attention, and I'm happy to take any questions.
Okay, first of all, thank you so much, Dennis. Hopefully you can hear me. I did have my microphone muted, but if it's all good now.
Yeah, I can hear you.
Perfect, wonderful. So we do have one question from the YouTube chat that showed up during the live stream. I wasn't exactly able to capture exactly when the question came in, so I don't know which slide it was exactly they were talking about. But the question reads, so if we're talking about virtual ECUs and emulators and cross-compilation, have you looked into how that affects the compiled code? You test a different binary, then that will be delivered on the target platform. What is the result of that?
Yes, so it's a good question. Let me go back to this slide. So it's a good question that depending on how we build this, if we compile it for the PC, you're right, we get a different binary. Some of the functions might look slightly different in the way it's built. compared to how the final binary would look on the ECU. So there might be some differences in particular issues that might occur, but in sense of the functionality itself, that should be able to be tested. That's what we see today already in terms of functional testing. So not fuzz testing, but the SIL systems here are already used today for functional testing. So we want to try to reuse those environments. They're building it today, testing it on virtual ECUs, testing functionality on virtual ECUs. So whatever we can build into that process and say, after you've done your functional testing on this virtual ECU, let's also do fuzz testing on it. If you want to be as close as possible to the target ECU, then what you can do is actually build it for the target CPU, take this hex file, and use a chip simulator. In this case, you should get a better representation of using the same binary and testing that on the PC. The difference is compiling for the PC is going to be much faster when you run it. The chip simulator will actually take some more time because it emulates or simulates the CPU of the target ECU. So a lot of those instructions are going to be a bit slower. So if you want to be more accurate in the testing, you use a chip simulator. It's going to be a bit slower, but you will get more accurate results. And that's also what you do sometimes for functional testing as well. If you're more interested in getting the speed and making sure that you can test more, then you can just compile it for the PC. So it could be a combination of all. Again, I'm not saying just use one approach, but look at the strategies of let's do as much as possible, maybe this approach, some functions, maybe we do the chip simulator. And as I said before, some of the functions we do have to test using the prototype ECU or the hardware ECU itself as well. So it's more looking at the strategies of how can we split the testing rather than doing everything here at the end on hardware. What parts can we move earlier and test using software?
Awesome. Thank you so much for the clear answer. I'm not an expert at fuzz testing or, debugging of ECUs or code itself even. But even I was able to understand that answer. So thank you so much for the great response to the question. It kind of sounds to me like there's a bit of a trade-off you have to make. Do you want to sacrifice processing power for a slightly more accurate, runtime environment for the code you're testing with the fuzzing, as opposed to being able to run more tests faster because you're using less resources for the emulation itself, is what I understood. Now, if I'm wrong, please correct me. But
yeah, no, in a sense, yeah. I mean, it's really of how you build the binary, and there might be some differences in how the binary is built. And the more accurate testing you want to do, the more time it will take because you have to have all of those instructions being simulated or emulated in that environment.
Right, that makes a lot of sense. All right, and then it looks like the same user just had one last question. It says, it seems you don't use sanitizers. Why is that?
So I'm not sure where in terms of if it's part of like the input, if that's the question, like on this input here. Like typically the systems here would have some kind of sanitizer. I mean, that's the idea that you want to try to avoid processing malformed input. So a lot of systems do have some kind of sanitizers, or let's say they do a CRC check, or they will check some fields to make sure that it's valid data before it's being processed. But you can also imagine there are situations where you have to process that data that you receive. Let's say if you use SecOC for secure communication over CAN, you're going to have the data and you're going to have the MAC. You still need to process that MAC to see if it is matching with the rest of the data. So I can create malformed messages here, either with malformed MACs or malformed data, which will be processed by that MAC verification function. So whenever you can, you should use sanitizers to look at the input data that's coming to the system, but there are also going to be situations where you have to process the data that's being received.
All right, wonderful. We've got one last question at the moment. This one just popped up. So this one sounds like it's more about the future for DefenseX. It's asking, what are the latest test suites for DefenseX? Can you provide a roadmap for any new protocols to be supported?
Okay, yes, that's a great question. I'm happy to to take that offline and share more details. But just to give a little bit of a information here. So we do look at the automotive Ethernet here as sorry, excuse me.
Take your time.
One of the protocols that we need to focus on more. Sorry, I've had this cough all day.
Nah, it's late. Don't worry about it.
So, for example, DoIP is a relevant new test suite that we started supporting. We also have support for PTP. We're also looking into, for example, other like protocols such as some IP and so on. So really looking at the Ethernet stack is one area. And I think that's where we see more requests coming as well as development or the systems shift from your traditional CAN to more Ethernet-based systems. Besides that, we also see more requests for communication with the backend, which is why I gave that example. We have these connectivity units communicating over TLS. You have X-Finance certificates, MQTT, JSON, and so on. So that's also the direction we see that we need to support those areas for communication as well. And there's also like some other cryptographic algorithms and so on that's being considered for extended support within our test suites.
Wonderful. All right, I think there's just one last one. Do you have energy for one more? Or I know it's already gotten kind of late. All right, so this one asks, so with RBS running and for monitoring the ECU for some PDUs which are not arriving at expected times, do we need to have some tolerance window, and what is the criteria of that window?
So that's a great question. I think it really depends on the target system and what is the behavior of that system and how critical, for example, some of those messages are. And this is what I meant before with you need to define what these threshold values or reference values should be, and they're going to be specific to that target system, depending on what happens if a message is lost, for example, or if a message is delayed. If we're talking about critical, like safety critical systems, your brake systems, airbags, and so on, it's going to be very critical if a message is delayed, and you may need to have a shorter tolerance of how much is allowed. If I fuzz the system, can I cause a denial of service attack that will, for example, block the airbag from triggering? Right? Can I delay it that long that I crash the car and afterwards the airbag will be deployed, but I can delay it long enough? So that's really depending on the target system. You would have very low tolerance for those systems, and you may have other systems where it doesn't really matter too much, like a door ECU. If the unlocking mechanisms is delayed a little bit, maybe you're okay with that. It could be a denial of service, but you still have to wait maybe half a second longer for the door to unlock. Maybe you don't have that strict of a tolerance for that system, but it really depends on each target system. Doing a TARA, like a threat analysis risk assessment, understanding how critical that system is in terms of the impact to safety and security, and then setting up the correct reference values or tolerance values and threshold values, so that whenever you're monitoring that system, you can say this is still within acceptable behavior, or this is unacceptable, and this is an exception. We have to do something about it. I hope that answered the question.
I think it was a great answer. So it doesn't look like we have any more questions at this time, so I think it's a good time to call it. It's a little bit late here for us over in Japan, but just before wrapping things up, I just want to remind everyone on the screen here, I have a couple of upcoming events that ASRG will be hosting. We showed this in the beginning, but for anyone that may have joined us a little bit late, just wanted to show this once more so you can save the dates, right? Put these into your calendars. We've got a presentation on the 29th about U-boot versus security. And then in August, we have 3 presentations coming up. We have the Security Cyber Garage presented by Accenture, IDPS from the vehicle to the VSOC presented by eScript, and we have V2RF, assessing the car's RF communications, given to us by Trend Micro. So if you have it in your schedule's availability, please by all means join us for these webinars. But I believe that is all that we have for today. Thank you so much for your kind questions and attention. And if you have any more questions, of course, I will be available through my own email. I think I had it here in this slide. Yep, right over here. So if you have any questions regarding automotive cybersecurity or ASRG, please feel free to reach out. You know, ASRG is a great resource that is eager to help anyone interested in learning more. So by all means, please don't hesitate to reach out to us. And once again, thank you so much to Kengo Oka for your wonderful presentation on fuzzing in the automotive cybersecurity industry.
Thank you very much, Kamal, for the introduction and hosting this webinar. I know it's late, so I really appreciate it. And thank you everyone for listening and for all the questions. Feel free to contact me if you have any additional questions. I'm happy to discuss offline as well.
And there you have it. Thank you all so much. We will see you all in the next webinar. Take care and have a good day. Bye-bye.
All right. Thank you, everyone.
はい、お疲れ様でした。